Hello, everyone. My name is Younes Belmazian. I'm a PhD student at Université Côte d'Azur. And today I will be presenting a paper titled Formal Analysis of the Count Mean Sketch with Conservative Updates. This is a joint work with Sarah Alouf and Giovanni Nadia. So first, we will see what is a count mean sketch with conservative updates. It's a popular randomized algorithm for approximate counting. Counting is a classical problem. You have a set of objects I, you have a stream ST of these objects. The objective is to compute the number of occurrences of these objects in the stream ST, as we can see in equation 1. Approximate counting wants just to estimate this cardinality at the expense of using smaller memory. The problem with approximate counting is that we have an error. Randomized means that the error is a random variable. Thus, we will be interested in the expectation and the CCDF, complementary cumulative distribution function of the error as a function of the memory. Approximate counting is used in multiple domains. For example, in caching for content delivery networks, it is important to know the popularities or estimate the frequencies of the catalog of your items. Unfortunately, this catalog can be very huge. Thus, we resort to approximate counting. Another point is the detection of denial of service attack. Someone is overloading a server with a lot of requests. So you need to keep statistics about all the items that are requested. It is also used in natural language processing to know what are the words that are used the most. The count mean sketch storage can be described as a matrix of counters, as we can see in this figure here. So it has dimensions W and D. D is the number of rows and W is the number of columns. We first choose D hash functions randomly, H1 to HD. These hash functions maps each item to a counter in each row, meaning that each item will have D counter, a counter in each row. The memory consumed by this algorithm is proportional to W multiplied by D. There are two algorithms, CMS and CMS-CU. We will start first by CMS. We present this simple example where the catalog has only 3 items, X, Y, and Z. And then we have this stream. The first request is to the item X. So how are we going to update this table or this storage matrix for the count mean sketch? We compute the hashes, then we simply increment the corresponding counters. It is requested again, so we do the same thing. And so on for item Y. And so on for item Z. At the end, we will have this table, and in order to estimate the cardinality of item X, we go to its corresponding counters, this one and this one, and we take the minimum. The error would be 1 because the real cardinality is 2, but the estimation is 3. The same goes for item Y and Z. Mathematically speaking, we first pick randomly D hash functions. This is from where we call it a randomized algorithm. The updates procedure would be as in equation 3. So CIRS is simply the counter associated for item I at row R. its value at time s. So we can observe that this counter is only incremented if the item I shares the same counter at the requested item. So this requested item could be either I, or it could be a different item. So in this approximate counting algorithm, multiple items can use the same counter, which causes overestimation in the error. But since each item has the counter, we only take the minimum for the estimation of the cardinality or the number of occurrences. For the CMS analysis, the error can be written as the minimum over the error at each row, as written here. These random Bernoulli random variables delta I, j, r of s are simply the contribution of item j to items i's count at row r and at time s. This is a building block of the error, so it is important to know its expectation if you want to analyze the error. The expectation can be computed as Pj, which is responsible for the request at time s equal to g, or 1 over w, which is the probability of having item I and j sharing the same counter. Now we look at the algorithm CMS-CU. So we have this state here of the filter. Then item y is requested. So we first compute its hashes. So we have at the first row, he has counter 2. And then at the second row, he has counter 1. So we compute first the minimum between the two of them, which is 0. Then we only increment the counter that is equal to the minimum value, which is 0. So as you can see, only this counter is modified, but this one is not touched, unlike CMS. Here the item z is requested. We do the same thing, and only the counter with the minimum value, which is 0, is incremented. We can see that the count mean sketch with conservative updates reduces the error with respect to just CMS. Finally, we will have this table, and then the estimation is similar to CMS. For the mathematical model, and then looking at the counter associated to item I at row R, we can see an additional condition here in red, which basically means that you only, even if another item shares a counter with you, the increment of this, he will only increment your counter if this condition is also satisfied. Thus the name conservative. The cardinality estimation is the same, and also the error. Why is it difficult to analyze CMS-CU? Well, because this building block of the error delta IJR has this additional condition that depends on the state of the system at time s-1. Looking at the literature, what can we use to understand this trade-off between the memory used by the algorithm and the error? We can use CMS analysis done in 2005. The problem with it is that it does not take into account the conservative updates. There is a work in 2012 that analyzes under this specific uniform distribution, and then the catalog size goes to infinity. But then again, this one is restrictive. We have also the work from 2015 that they provide probabilistic bounds on the error. We prove that their bounds are trivial in this specific setting, which is important in the use of approximate counting, that the dimension of the CMS should be smaller than the dimension of the catalog size. As I'm positive. The other work is a recent work in 2022, and it studies the uniform distribution. Again, it's restrictive. So our main contribution is upper bounding this building block of the error, delta ijr of S. So here we can observe two important terms. We have this term here that depends on S, and then another term that does not depend on S. So this term that depends on S converges to 0 as S goes to infinity. So we can ignore it for now. Notice that here, the most popular item is 1 and the least popular item is n. PG over W is nothing but the bound for CMS. So this gamma ij is actually an attenuation term taking into account the conservative updates. And actually, we only have a bound that is better than the CMS when the item j is less popular than I. And in this case, we will have a bound on the delta ijr of S that is that is proportional to 1 over W to the power of D. Whereas in the CMS case, it's proportional to 1 over W. Now that we have this building block, we can have bounds on the expectation of the error, but also bounds on the CCDF of the error as a function of the rank of the item. It means that the most popular items will have, starting from this lemma, will have better bounds, and then the least popular items maybe won't benefit from this lemma. To test our results, we do an experimental benchmark. So in the synthetic setting, the catalog of items is 1 to 10 to the power of 6. Then each item has a probability of being requested that is according to a ZIF distribution. Then the results are averaged over the 100 experiments. So for each experiment, we have a different stream STI, and then the number of requests on this stream are 5 multiplied by 10 to the power of 6, 5 millions. Then we have this default configuration for the sketch, and we pick each time different hash functions. For the real trace, what we do is that we have that the set of objects is the Wikipedia pages. Then this trace contains 10 million requests. We split it into 10 chunks. So the first chunk we use it to estimate the probabilities, because our model assumes that we know the probabilities. And then for the remaining 9 other chunks, we use them for the experimental evaluation. The sketch will have this default configuration for the Wikipedia trace. So in this plot, we have the normalized expected error with respect to the length of the stream as a function of the rank of the item. 1 means the most popular, and then 10 to the power of 6 is, in this example, is the least popular item. So we observe that both in the synthetic and the real-world trace, we have that our formulas can capture that the most popular items barely experience any error, which is the one in blue, and the green one is the experimental, whereas all the other works are failing to capture that. For the CCDF again, here we evaluate the CCDF as a function of X, and then we look at the probability that the error is larger than X. This is for the synthetic, we look for the item I ranked 100, and then for the Wikipedia trace, we look for the item ranked 50. Then again, there is a significant difference with respect to the other works. A use case of this approximate counting or CMS algorithm is detecting heavy hitters. So heavy hitters is this set, all the items that has a count that is larger than a fraction of the total of the length of the stream. And then hat H is our estimation of this set. So the precision would be the length, the cardinality of H over the cardinality of hat H. In these plots, we show the memory required as a function of the target precision. So then we use our formulas to predict what is the memory for a given precision. We compare here with the CMS analysis, and we observe that our formulas allow to have a significant reduction of memory, actually. So for instance, here for the Wikipedia trace, and for a target precision of 97.5, we require a memory that is smaller than 0.2, whereas the CM05 requires a memory that is almost 1. So we have more than a factor of 5, actually. Finally, our paper allows us to have a better understanding of CMS-CU benefits under a heterogeneous request process by showing that the most popular item barely experience any error. It also allows us to have better configuration rules for estimating the precision in detecting heavy hitters. Thank you for your attention.